Yes, so Srikanth students, let's discuss what is steady flow. Well, imagine that there is a duct or there's a pipe. The fluid is flowing in this pipe. This is a pipe with varying cross section area. Let's say at end A, the area is A1, and at end B, the area is A2. Well, the fluid is flowing in this direction, flows and then flows out. Well, it's a streamline flow. No streamlines are cutting each other. We want to understand and define what is a steady flow. So students, let's imagine one, two, 3 points. In these 3 points, we can easily see that because as the fluid is flowing in this pipe or duct, the area of cross section is changing. It's actually decreasing in the direction of fluid flow. So there will be variations in the velocity also. So hence the velocity at point 1, at point 2, at point 3 will be different, right? According to the continuity equation. So when the diameter is more or the cross section area is more, the velocity would be comparatively less. And here the diameter is less, cross sectional area is less, obviously velocity will be comparatively more. All right. Now we are imagining a incompressible fluid. What is the meaning of incompressible fluid? A fluid which cannot be compressed. That means the density is not changing. Obviously, when the fluid will be compressed, like in this piston, and you have a cylinder, this piston and cylinder. Let's say the air is there in this. Obviously, when you press this piston, the air will be compressed. So the density of the air will increase, right? But imagine instead of air, there's water in this. We can well assume without any much error that the water is incompressible. No matter how much force we apply, we will not be able to compress the water, okay, or very, very less, even at very high pressure. So that is the meaning of incompressibility. The density is not changing. So the fluid is incompressible. Now there will be thousands and lakhs of fluid particles which will pass through point 1, let's say in 1 hour, or maybe in 1 minute or 30 minutes, whatever it is. There will be thousands of fluid particles which will pass through this point, right? Now, imagine that all the fluid particles which are passing through exactly one point, let's say the size of point is equal to size of the particle. So the velocity of all the particles which are passing through point 1 is, let's say, v1. All right, let's say in 1 hour. Similarly, as we know that the velocity is changing, so let's say at point 2, the velocity of a fluid particle is v2. Well, that particle comes and passes by in fraction of second, but all the particles, thousands and lakhs of particles, which in the same time interval, 1 hour, are passing through this point, right? Their velocity is all same, that is v2. Their velocity is not changing with respect to time t. Similarly, all the fluid particles at point 3, they are also having constant velocity v3 in this time duration. So from this judgment, we understand two things. Number one, the fluid velocity. Fluid velocity, like so many other parameters, is one of the fluid parameters, right? It's flowing parameters, fluid parameter, or you can just say fluid velocity also. The fluid parameter or fluid velocity is not changing with respect to time. We have observed it for 1 hour 60 minutes. Means the fluid velocity with respect to time at a particular position is not changing. You can take any point, not just 1, 2, and 3 point, any point in this conduit. If you concentrate your attention on that point, at that point, the fluid velocity is constant with respect to time. That means velocity is not a function of time, right? What does that mean? Only when the velocity varies with respect to time, then only we can say velocity is function of time. It's not the case right now, right? So dv by dt would be equal to 0, right? So second thing, what we have observed is at different locations, the velocity is different. All right, that means the velocity is a function of coordinates, or you can say location. The coordinates may be x, y, z, because it's a three-dimensional fluid flow. So we can say, like x is changing along x-axis, the position is changing along y-axis, the position is also changing along z-axis. So at different location, the fluid velocity is changing, but the fluid velocity is not changing with respect to time. Such a flow where the velocity is not a function of time means the velocity is not changing with respect to time, but the velocity can change with respect to location, is known as steady flow. Very, very interesting things. One more thing to add on this, students. If you have a flow, let's say the cross-sectional area of this pipe is same. Let's say this is the pipe, its cross-sectional area is same, right? If we neglect the no slip conditions here, which obviously we cannot neglect, imagine that if we neglect no slip conditions, the boundary layer, and if we imagine that the fluid velocity is same at all the points, then also the fluid flow is steady flow. Then the fluid flow will not be a function of time and will not be a function of location also. Well, such a fluid will can also be hypothetically imagined as a steady flow. But then it is difficult to imagine this, right? Because here the no slip condition will exist. So the layer of fluid which will be which is adhering to the internal surface of the conduit, would be stationary. And as you go this way or up, the particle which is traveling at the center would have maximum velocity. So students, this is the concept of steady flow. Once you understand steady flow, it is an important assumption in the derivation of Euler equation or Bernoulli equation or even equation of continuity. Thank you very much.